So, good morning, folks. So, today is our last lecture. It's also the last day for your group work. I will repeat what I told you yesterday in the morning. So if you forgot it or if you were not here at the beginning of last lecture, tomorrow you have the presentations and you have a time slot allocated for your group of 35 minutes, which is divided in 20 minutes for your presentation, 15 minutes for questions, okay? So we will start at 10 and we will end at 5:30. Pay attention that your presentation should be professional style in the sense, not in the visual sense, but in the sense that ideally one person or maybe two persons giving the presentation and showing the results and showing the interpretation, the biological meaning and perspectives, and just telling us how great it is to work on that. So that's for tomorrow. And so today, usually we officially say it's the day to prepare the presentation, okay? I know that's not true, okay? And I know that usually, at least in a part of the day, people are still working on the model, if not all the groups, some of them are still working on the models. There are people that maybe are starting a new model in the afternoon and so on. But anyhow, tomorrow, please be here at 10. Have your presentation prepared. And again, let me repeat. We prefer presentations in PDF, but you can also use your preferred software like PowerPoint, okay? You can use the computer that is here, the Institute's computer, or you can use your own computer. But what we really, really want is that you test if your presentation is working with the projector. Therefore, before we start the presentations, it will be blocks of 3 presentations. In the morning, 3, then a second block in the afternoon with a break, and then last 3, because we are 9. So before the starting of the block where you will give your presentation, I ask you to test things, because otherwise it always happens that, oh, it is not working, oh, whatever, blah, 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 and so on, so on, so on. So I really would like you to test things. It is also nice if you can give us a copy if you want. We can put this on internet, but I mean, it's up to you, okay? So today, we will have a soft lecture, a lecture which is shorter, and it's just an illustration of the kind of applications that we can do with population dynamics, and even with one very simple model, get some insight in the real biology and the real patterns that you see in nature. And so we will talk today on vegetation dynamics in actually semi-arid regions of the world, okay? And this will take us to models that have a property which physicists call hysteresis, and which ecologists call alternative stable states. Or you could also name it bistability. These are the key words. And okay, then there will be the glory and the misery as usual. So just for you, obviously it is semi-arid regions in the world are widespread. You find it on all continents are arid and semi-arid, okay? So even here you have in Brazil, the same semi-arid regions in northeastern Brazil. Here you have Patagonia, here's the Atacama, which is actually a desert. And here is the Kalahari, here is the Australian desert and so on. Sahara, here is the arid region of like Arizona and northern Mexico, and here is the Gobi, and so on, and here's the super desert, which is the Arabic Peninsula, and so on. So there are lots of places in the world where you have semi-arid regions, or sometimes you have actually arid regions, arid in the sense that nothing is there. It's like Sahara or Gobi. No, Gobi has some something, but certain parts of Kalahari, then there's no plants at all. But even in these cases, you have usually something. I mean, at the borders at least, it is the transition is what we would call a semi-arid. There's some rain, there's some plants, and but not much. Okay, so we will be interested in this case and to model the dynamics of vegetation in these situations. And here, yeah, it's just an illustration for our particular case in Brazil. Here, it's just a semi-arid region. So, you know, when I talk about semi-arid regions, you have I think you have a picture, okay, what kind of things I'm talking about. So, if we now want to model the dynamics of vegetation, okay, so we have to start with what are, so you will try to model the vegetation how? Well, there are many approaches that you could go for, and we will take that, we will just use as our vegetation, the variable describing the vegetation by the biomass, right? So I'm distinguishing different species of plants, okay? So I'm just looking for the biomass. Could I go for something like putting different species? You could, and probably you could do something like species which have different behaviors or something, and so on. But, well, this would be an elaboration, and it's actually a research area. People work. As I told you, next year we have even a school of this, because Ricardo Martinez, who is now coming here to the institute, is actually has a research line on vegetation patterns. So it's a very active area, and what I will show you has been done, I think 20 years ago, more or less 20, no, even maybe 30 now. So, which is the very basic thing, okay? So, biomass. So, how is the biomass regulation? Is it top-down or bottom-up? In this case, it's clearly bottom-up. It is limited by the availability of water. That's almost the definition of what is semi-arid region. Semi-arid region, there's a lack of water, and water is the main limiting factor for the growth of vegetation. Okay, so sounds natural. Okay. So we will build a mathematical model about the relations between water, but what water are we interested? We are interested in the water in the soil, which is the water that can be absorbed by biomass, okay? So you already see the picture. The biomass will act like a predator of water, okay? Good? The consumer of water, okay? Water will be the so to say, prey. But well, you know, every time you have predator-prey, consumer resource things, you have to know if this is a linear process, if there are non-linearities, and so on. You have been working with this kind of thing in your group works. I mentioned this at the end of the lecture on predation, so there can be something. And then there's the particularity that water is an abiotic. It is not a living thing. Therefore, water does not reproduce. Okay? So we have to take this into account. So, very nice. Okay. Okay, that's just what I told you. So we will have two variables. One of this is the W, which obviously is the water in the soil, water in soil. And EU is the biomass, okay? So the idea is that it's kind of proportional to the area where the, okay? Because, but anyhow, it's in biomass in a certain place, okay? So, so we have to make a modification of predator-prey dynamics that takes into account the particularities of this thing, the abiotic nature of water and the rate of consumption of water by biomass. There should be a law for this. There should be something that describes this. We will consider the precipitation. So, we will consider the precipitation. Yeah. And this looks, as it abiotic, it can come from nothing, okay? If you don't have water, you can have water precipitation. It's not like a biotic thing. A biotic thing, if you have zero population, there's no generation out of nothing, ex nihilo. No, there is not something like that. So abiotic has spontaneous generation, which is just some coming from some external factor. So okay, so let's just so this goes under the name of Klaus-Meyer model, and so the idea is, okay, the rate of change of the amount of water in the soil should come from precipitation as the positive. That's the only way to have new water in the system is by precipitation. And I'm considering a constant precipitation. So again, pay attention here. The A here is not multiplied by W, okay? Because it's abiotic. It comes from the sky, okay? From out of the system. So, and I'm considering this constant. Then you'd say, well, obviously not constant. It rains some hours only, okay? So again, time scales, spatial scales, okay? Over, if you take your data in, say, months or years, okay? So you can kind of take the average value. And this is what you expect to have a real effect on the patterns of vegetation, okay? Because there will be no effect from the, just if it rains a lot today and less tomorrow and then again a lot. So you take the average. So we are thinking about the time scale, which is this time scale where you see changes in the biomass. And this is on the, typically on the scale of at least 1 year, okay? So then there is evaporation, which is proportional to the amount of water, because you can have only evaporation if there is some water to be evaporated. So this is just therefore a kind of mortality term of water, okay? And then you have to write the absorption of vegetation, so of water by vegetation. So here you see I have something curious here. It is a cubic term. It is the square of U, and remember well, U is the biomass times the amount of water. Where does it come from? Well, that's a thing that you can study in the lab. Right? If you have a lab, you can have soil. You can have different kinds of soil, and you can put biomass, and then you can study the absorption of water as a function of the amount of biomass that you put into the system. Okay? So that's can be done experimentally, and people are surely interested in this because it's very applied. Okay, I mean, if you are going for agriculture, then it's a useful information to know how much water my biomass absorbs in general, and in particular in this case of arid regions. Okay, so this is an input of the kind. There's some reference that will tell you that this is the good law. Okay, so and the important fact is, you see, it is not just U times W. It is U squared, okay, which introduced a new kind of nonlinearity. Very well, so I have the equation for the amount of water in soil. There could be other things, like there is extension of this model take into account, for instance, that the terrain inclination may be important, okay, because then you create flows of water. So they can take a lot of things. You can also consider the diffusion of water in space, in the soil. Therefore, you go for a partial differential equation with the spatial parts and so on. So people have studied this. But we will stay here, for instance, with the simplest thing. Now, for the biomass, well, no water means so the water is an essential nutrient. Therefore, in the absence of water, you expect actually only the natural decay. Okay, so this is just a natural decay of biomass. And that's the water that has been absorbed by the plants, which has the same functional form, the same expression like this, but only with a different constant, because you have to convert water to vegetation. Therefore, it's not the same constant. Okay, it's not like in epidemics, which a person is susceptible and the same person gets infected. There's an efficiency 1. Here, no, it's not 1 liter of water gives you 1 kilo of biomass. It's not like that. Yeah, so therefore there's kind of conversion factor E here. So I have 2 equations, and that's my model. Pretty simple, yes? I mean, with only two equations, very simple model. We can go for the analysis of this, so let's go for a little bit more technical part. So, okay, I have a model. Let me put it here. Okay, let me go back here. I have 2 equations. I have parameters A, B, C, G, E. 5 parameters. It's a lot. But I can reduce the number of parameters. How? Rescaling parameters. As the same thing as we did to study competition. The equations, the Lotka-Volterra competitive equations, have been studied by the magic of transforming a system with 6 parameters to a system with 3 parameters, and this was so nice, okay? Because this really... So I can do the same thing. I have 3 possible rescalings. Okay? So I can actually... I can actually transform this equation, system of equations, in a system of equations that will depend only on 2 parameters. So how do I do this rescaling? You could think about a-dimensional variables and so on, but actually, what I will show you, I will show you the result, but it's a lot of calculation. What you take is you define a new variable, capital W, capital U, and sometime I will call it capital T. So new variables that are proportional to the old ones, which were the small w, the small u, and the small t. These are the original variables that gives you your biomass in units of biomass, your water in terms of the amount of water, actually with dimensions and so on. But I can multiply this by a factor, alpha here, beta here, gamma here, any factor, okay, which transforms the old to the new and vice versa, okay? So I'm allowed to do this. So I can just do alpha, beta, and gamma. And then I put this into the equations. I substitute the variables, the old variables per the new ones, and then the system will depend on the alpha, beta, gamma. And I fix arbitrarily alpha, beta, gamma so that my system of equations will have some terms, will make some parameters disappear, okay? So using the arbitrarity of the choice of alpha, beta, and gamma. So this goes in this way. Here are the equations. These are the new variables. This is capital W. I'm using quite a factor here, yeah? And here also factor, and here also factor. So you could ask, well, where did you get out with it? I mean, could I guess that? No, nobody guessed this. I'm just showing you the result in order to make a long calculation short, but it was done like that. You just put some parameters here, and then you give parameters alpha like this. So this would be my alpha here, yeah? And this is my beta, and this is my, the B is my gamma, okay? So if you do this and you put this into the equations, I will get a system of equations with only 2 parameters, which are A and B, which are combination of the old parameters. So now my system depends only on 2 parameters. So the interpretation of the parameters, well, the best way of looking at this is, the parameter A, it's actually proportional to the precipitation. So that's a non-dimensional measure of precipitation, okay? So that's a rescaled variable of the precipitation. So when I say, let me change A is change the precipitation, okay? We will go for a bifurcation diagram where we want to know how the system behaves with different values of A. Different values of A can be thought as coming from the change in precipitation, okay? So, 2 equations, only 2 parameters. Nice. This will allow us to do some nice analysis because it really turns out to be simple, okay? So 2 equations, 2 parameters. We know how to do this. What do we do? Qualitative analysis of dynamical systems. So, in this case, it's easy. I will be interested in the behavior of the system and the UW plane. And the first thing, starting point, will be looking for the fixed points of the system, the values of U and W, constant values of U and W, such that the system of equation is satisfied. Okay? So we want these special points, let's call it special points, with this little star here, such that water and biomass are in equilibrium of stasis, of static equilibrium. And well, if you have here the equations, if you put 0 for the derivatives, you get these equations from the right-hand side of the differential equations, okay? So if the equations are satisfied and the system is not changing in time, then you need this, and this is a system of equations which is two equations. It's algebraic, nice. You could say it is. It may have some nonlinear behavior and so on. Okay, so it is not a quadratic system that we can solve. It will give you, if you substitute, if you solve for, say, u or for w and substitute in the other equations, it will give you a third-order polynomial, which we don't want actually to get the explicit solutions, even if you could using Cardano's formula. But obviously, we don't want this, okay? So we want analysis and so on. But let us look at it. So I can, yeah, sure. Okay, actually, we can solve the thing. So, okay, excuse me, I really forgot that we have the solution. Okay, so it's easy. It turns out we can solve the algebraic equations, and what happens is we have 3 fixed points. So if A is smaller than 2 times B, the only fixed point that exists is this one. And this one says what? That the amount of biomass is 0, and there's a certain constant volume of water in the soil. This is a desert. That's the desertic solution. Okay, no biomass at all. Okay, so, but this solution is always there. It's always a solution, even if A is bigger than 2 times B. Okay, but if A is bigger than 2 times B, you have 2 new solutions. So if A is bigger than 2 times B, you have 3 solutions. This one and these 2 solutions. This one is a desert. This one isn't a desert because U is not 0. There is vegetation. There is a static equilibrium between vegetation and pollens. So this would be, if it were in epidemiology, it would be an endemic state. Yeah? And so our model has the possibility to describe, as solutions of the model, a situation where there is no biomass, it's a desert, and can also describe a situation where you have vegetation cover, biomass different from 0. Okay? This here can be taught as very natural thing because A is the precipitation, yeah? And B is connected to the process of absorption of water by the plants. So A being very small means there's no enough rain to sustain biomass. Okay, that's what it means. Okay, if A is too small, then you don't have enough rain to sustain biomass. Okay, but now the thing here is, if now A is actually bigger than 2 times B, I have, for the same parameters, for same A and B, I have 3 solutions. Okay? I don't have one attractor. I have 3 solutions, 3 fixed points. And then the question that arises naturally, sorry, which arises naturally is which fixed point will be actually attained for a long time behavior. Which fixed points? I have 3. I have a desert, and I have 2 fixed points with vegetation and water. Okay? So let me stress again, which is very important. I think many times people, when I discuss alternative stable states with ecologists and students, and not here, but in the ecology department, people do make a confusion of having many solutions to an equation, and but with different values of parameters. Say we go back to the Rosenzweig-Mercator equation, okay? So the carrying capacity is very high, you get oscillations. The carrying capacity decreases at a certain point, you have a fixed point. So you have oscillations and fixed point. Is there something similar to this? No, not at all, because it's different values of parameters. If the carrying capacity is below a certain critical value, oscillations. If it's below its fixed point. If it's above, then you get oscillations. Here it's different. Why? For the same, once given that A is bigger than 2 times B, for the same A and B, which are the only parameters that I have in the problem, I have 3 solutions. This one, which always is fixed, and these 2 ones. So for the same parameters, okay? So that's the point. And therefore, if I start with a given situation, where I give an initial condition, I want to know what's the long time behavior, and what is, and if, well, I can anticipate long time behavior is that the system will go to a fixed point, okay? But the question is, which fixed point? So, okay, that's what I told you. So now what we have to ask first is stability. Okay? So the first thing is, remember, maybe we have 2 unstable. Then the question is trivial. Okay? But so you can go for stability analysis, which involves certain amount of calculation. So the linear stability analysis results, so I'm skipping the analysis, I'm just giving you the results because I decided not to do all the algebra. So the fixed point, which is the desertic fixed point, turns out to be always stable in any case, okay? So, so it is here, even if this is exactly the should be bigger than. In any case, the desertic fixed point is always stable. You get to desert, you stick to it, you don't recover. Catastrophic. Catastrophic, yes? Yeah. So we have a completely stable desert. Then you could argue, oh, well, this is not so exactly, but well, okay. With the biology that we are considering, we are not considering people coming artificially modifying the soil and whatever, for instance, what people have done in Israel and other parts in California and so on. But okay, with this natural scenario, the desert is a stable fixed point. Well, somehow this also sounds okay. Because why? We talk about desertification, okay? But desertification means, okay, you have a part of the part of the world where you have biomass and you have less and less, and you are becoming a desert. You don't hear about naturally a desert converting to a forest. Okay? Naturally saying, okay, the Sahara is disappearing, and it's becoming a forest. Yeah, you don't hear this, okay? Because it doesn't happen. The desert, the forests, or in the case of Sahara, shrublands, can become a desert, but not the other way around. So it's okay to have in a first approximation that the desert is a fixed point, okay? That it does not naturally gets unstable and it becomes unstable. So then I have the two other fixed points which exist only if A is bigger than 2 times B. So given that A is here, 2 times B, given that one of the fixed points is always unstable, and the other fixed point is stable provided that B is smaller than 2. Okay? So this comes out of the analysis. So B is smaller than 2. Well, a rough interpretation is B is the absorption rate of water by the plants, by the biomass, and if the biomass absorbs very quickly, absorption is very high, so then the water that is not, there's no enough replenishment of water in order to sustain the biomass. Okay? So we will take for granted this thing here, because that's when we have an interesting situation. B is smaller than 2. Okay? Otherwise, if B is bigger than 2, then you have only one stable fixed point, which is the desert, and end of story. Okay? The good and interesting stories come when you have B smaller than 2, and if B is smaller than 2, then I have the desert situation is stable, but this other one with biomass cover is also stable. And therefore now, given a certain initial condition, where will I get to him? So, one way of depicting this situation is drawing things. Where is the... So let me explain this diagram. So we want the equilibrium value of the biomass, okay? So, as a function of the A, and A, remember, it's the precipitation. It's the non-dimensional way of describing the precipitation. If I had continued with the original variables A, this would be really the precipitation. Here it's just the precipitation value multiplied by some constants. Okay, so. Stability, you have a fixed point, you give infinitesimal perturbation, and you look if the perturbation grows or decreases of the variable. Yeah. So the idea is you have a solution. Say you had U times W. Okay. You have here a certain fixed point. Okay. Then you say, okay, if I sit exactly on this fixed point, I stay there because that's the definition of fixed point. Now, I want to know if I perturb this solution and I go here, nearby. So if I go nearby by an infinitesimal amount and I drift away, I say this fixed point is unstable. Why? Because you would never have a situation without perturbations and exact values and so on. Therefore, an unstable fixed point is not observable. It's not something that you will see in the nature, okay? And if this perturbation goes back in the same, I mean, by the dynamics of the equations, goes back to the, and approaches the fixed point, then I say that the fixed point is stable, okay? That's the meaning. Okay, this is called the usual stability, local stability analysis. So I introduced a new word, new buzzword, like local stability analysis. Why? Local means I do infinitesimal perturbations. You could ask yourself, okay, but I don't want an infinitesimal. If I take this and take not very near, I take it away for a long time, okay, then you could also say, well, this can go back or not. If everything here on the phase plane goes back to the fixed point, then say the fixed point is a globally stable. It's a global fixed point, okay? But, well, we are not, in this, actually, we will see that there are no global fixed points here in some cases. But when I talk stable and unstable, it's locally stable, okay? It's not globally. So, okay, so I want to know how the biomass depends on the precipitation. So there's a clear thing. If A is smaller than 2 times B, you have the only solution is the 0 here. That's the only solution, okay? Now, I told you that the desertic solution is also stable when you when A is actually bigger than 2 times B. Therefore, there is a stable solution, which is the 0 on all the line. This is a stable solution. So there is, when I talked about epidemics, I just mentioned at a certain point when you have this R0 smaller than 1, you don't have the epidemic. R0 larger than 1, you have the epidemic. And rephrase this, that R0 smaller than 1 means that the disease-free situation is stable. And if it is bigger than 1, the endemic situation becomes stable and the disease-free unstable. And I call this exchange of stability. I don't have exchange of stability here. You have to talk a little bit louder. Yes. The border become? Ah. Yeah. So, yeah, I will show you exactly. You are asking me to do what I will do on the blackboard. I mean, here in this, for this model, we have only these 3 fixed points and their stability properties. Obviously, you could say the desert could not be completely stable because we know that you can intervene and somehow and so on. So you can build a better model. That's the simplest model. You can put something else and then you get things. So, but let us look here. Okay, I think you didn't formulate the question in these words, but yeah, you know, once A is smaller than 2 times B, and then you go and artificially increase A, it's of no value because they stay in a desert. Okay, I mean, this solution is stable. If you perturb it infinitesimally, in the sense that maybe the precipitation increases, maybe this was just an area of drought, but then you had climatic change and it rains. But still, if you're on the 0, a small perturbation of the 0 will not give you back the forest. It is stable, and that's the drama. Okay? So, now, if A is in this part, if it is bigger than 2 times b, I have another solution which is stable, which is being drawn here, okay? Which is something like that. So for every value of a, okay, I have also a solution which is stable and which represents a certain amount of biomass which is non-zero, okay? Equilibrium with biomass, okay? This would be forest, shrubland, or whatever, okay? Savannas. So, now, this means that in this region here, I always have 2 possible solutions. I have 2 possible solutions. So, and then obviously you can't also put pose the question that, again, if I start with a certain biomass, will it be attracted to this one or to that one? Okay. So in ecology, we call the possibility that having for the same values of A and B, 2 possible situations. One is a desert, the other one is vegetation coverage. We call this alternative stable states. In physics, we say the system is bistable. Why? Because there are 2 fixed points that are stable, so it's called bistable. Even if there are many fixed points, people continue to use bistable. And so this is the jargon that is used. So if you have been working with ecological problems, and even not ecological problems, even environmental problems, alternative stable states is a buzzword. I mean, it's something that happens all the time, and so on, and so on. And you hear this, oh, the alternative stable states. Oh, there are alternative stable states. Okay. So, and this is important. Okay? And I will show you why. So, now say that what happens is there is a value, there's a separatrix of in the value of the biomass, such that if I start with biomass corresponding to this value here, okay, which is not a value, okay, biomass here, it's not possible, okay. Let's say I start with here. I have to go either this way or that way. So there's a line, imaginary line here, okay, such that initial states that are above are attracted to this one, initial states that are below are attracted to this one, okay? So there's a kind of imaginary separation which gives me what is attracted to one and it's attracted to other. So physicists will, maybe if you have done a very elementary class of nonlinear dynamics, you have seen, or people like to use this in quantum mechanics, actually, example, you have seen what people call a double well, okay? When you have a particle here, okay, which may move on the double well, okay? So, you have many situations, depending if you put friction or not. But if you don't put friction, it's actually not nice. But put a little bit of friction. So you have 2 stable points, which are this ones, okay, which are in the bottom of the wells, okay. And then obviously you could say, okay, but where will my particle go? Well, the answer will be if you start here, you will go here, and start here, you go here, and this side, you go here. Depends a little bit on how strong the friction is, but okay, let's say it's not allowed to start over this. You don't start. Anywhere here, you get back, so you get to this point, anywhere here, you get to this point, and this is the separatrix, okay? So that's a very visual and easy to understand situation. So exactly what we have here, not exactly, but it's similar to what we have here. We have 2 fixed points. For every value of A, we have 2 fixed points here. And some of the solutions are attracted to this side and some to the other side. And there's a line. It's a line because A, it's the parameter, okay? So that you could consider all the, for a given A, there's a point, and obviously this makes a line if you consider A, if you sweep all the A. So this is the main result that you get, but let's extract something more interesting from that. So let us fully go for the consequences of this result. Okay. I will, instead of just reading this, which is dump, I will explain you on the blackboard, which everything can be seen here on this plot. So now, say you are happy and you live in a world with biomass, and you are here. You are in equilibrium, you have biomass, equilibrium, water, biomass, paradise. Okay, now say over a long period, we are talking usually tens, decades or centuries, except if you look for climate change now, which is on an yearly basis. But on long time periods, A can be variable, okay? So even if you take A as the average of the precipitation of the year, you know, it will be variable because they don't have exactly the same amount of water every year. But, well, you could say, okay, even it being variable, it can correspond to a certain regime, yeah? Something like it rains a lot, or it's a more, it doesn't rain in that part, and so on. So it is conceivable that A can be changed very slowly. Okay, so if it goes over the time, and changes slowly, this is still a good picture because the equations, well, the equations were solved with A equal to constant. Okay. So if A is not a constant, I should have near solutions. But if A varies slowly, this is still a good approximation. And so now say you started here at a certain point, let us call R star, which is our, what did I call it? A something. Okay, so A dot. You start here and say, if A increases, you just get more biomass. But if it decreases, you go here and biomass decreases. But it comes to a point here. And it decreases further, it goes immediately to 0. So the approach, first of thing, there's a tipping point. Okay, now that's also a word that you see all the time. Tipping work in climate science. So what is a tipping point? There are two different concepts of tipping points. One of them is this one, which says that I have a sudden change in my system. I had a certain amount of biomass, and now I don't have any. It's not continuous. It is sudden. Okay? So, and this happens if you go for the full equations with a variable A. The point is that you have a certain solution, and which can vary a little bit if A is variable, and then this drop goes on a very swift click and a very high velocity, new time scale goes very quickly. Okay? So I got a desert. So my trajectory here, let me find something with the color, but this is not good. So we have no. So I started here, I got here, I went down, and still here, and then maybe this change was was a cycle, climatic cycle, and then starts to rain again. And you get back with the value and crosses the critical point. And you go back to the previous situation. You don't get back here, you get back to this. Therefore, you start with a certain precipitation, you pass the tipping point, and you go back to the initial precipitation. You don't get back the same solution. You get a new solution. There's a gap here. There's a difference. So here, biomass is 0, and here it was not 0. Why is this? If you go here and you have small perturbation, this is a stable state. Okay? So then you stay here, even making small perturbations. But if you drop down, because your A was not high enough, if you drop down to the desert, when you come back, this is also a stable situation. Therefore, it will not jump here. Okay? So you have actually a gap here, and this phenomenon is called hysteresis. Okay? It's very common comes from magnetism. Okay? Yeah, it's like you have something that has no magnetization, you put a magnetic field, it gets a magnetization, you turn off the magnetic field, and it stays magnetized. So this is the typical thing that you learn in your first or second year in college. So hysteresis is something that is very important to look at. And so this is an example, okay, where we have hysteresis, you have peeping points, you have all the things that are very popular today. Okay, hysteresis. People don't say hysteresis because only physicists say hysteresis, but people will say, I don't know, we'll invent some funny name. But it's hysteresis, bistability, alternative stable state, tipping points. All of this is here. Okay, so. And this could only happen. Okay, let me just, what was I going to say? Okay, okay, there's an example, actual example for the glory and the misery of the glorious. This is vegetation cover of certain regions of Sahara, which were covered by fossilized pollen in the soil. People are very smart, yeah? You get something to have a proxy of vegetation cover of a certain region more than almost 10,000 years ago. This is smart people. So, okay, you can read this in Trends in Ecology and Evolution. You can find this paper, very famous paper. So you have a certain amount of vegetation, and you drop down, and you get very smaller amount of vegetation, okay? And so there's a kind of drastic transition, which looks like what people call the catastrophic transition, okay? That's also people like working on this, like a guy called Martin Scheffer, like this name, catastrophic, okay? So, and this happens in many other systems. Well, the misery would be that this model is obviously a little bit too simple, because if you look at actual deserts, this is Gobi and this is the Sahel. It's the region of transition between the tropical Africa and the Sahara. And well, there are shrubs, yeah. So it's all, Semiarid is not zero biomass, okay? It's a small biomass. So the better models should somehow explain that the biomass is not actually zero, but there's something. And well, there have been experiences of artificially rebuilding vegetation on desertic regions. So you'd expect that given good conditions, you could do something, in which case, in our model, the only thing you have is a precipitation, but you would expect that, well, for very high precipitation, okay, maybe there should be there should be a way of getting back here. which would mean what? That this solution of a desert is only stable up to a certain point. If the precipitation is large enough, you can go back. Okay, this would be a more realistic model. You have to know all better about the processes of water absorption in semi-arid regions. You have to put new biological phenomena to get this, and you would expect something like this. This is the zero, and the zero is stable only up to a certain point. This is the a biomass non-zero situation with biomass coverage, and here this region is pretty much similar to this situation. Okay, you can drop here, but in this in a more realistic model, you would have something like this. When it rains enough, you can go back and have a backward transition. Okay, this would be nice. Okay, so this is more realistic. I'm not even writing down the equations because, well, we will not become specialists on vegetation dynamics here. Okay, so people have done works on that. People have done works taking into account the spatial dimension, which also introduces new phenomena and so on and so on. But the basic phenomenon is presented here, and there is a way to give you, from an example, an illustration about these concepts that have been around and been talked about by authorities and so on, and usually in the present day they are seen connected to climate change. So let us make a retrospective view of why we have this situation and why. So let us get back to the equations. Okay, equations. We like equations. Oh yeah, everybody's already comfortable with the equations after all the course. So where are my equations? Okay, here are the equations. Okay, these two equations. So if you go a little bit for the algebra here, and you will see that this term is very important. If you have, instead of the square of u, only u, linear in u, no bistability. So this comes from nonlinear interactions, nonlinearities, okay? And which are usually called feedback loops. So that's also something that you hear in every non-technical discussion about climate change, and it's actually very important. But what is a feedback loop? Okay, let's look for water here, okay? So water is being depleted by biomass, okay? So biomass uses water, increases the biomass. But increasing the biomass, say the biomass had doubled, the consumption rate is not linear. It will not be doubled. It will be actually 4 times because the square. And this depletes more and more the water. And this enhances more and more the consumption, which will again increase non-linearly the consumption of water and so on. So that gets a loop, okay? So you get into a loop. So that's what people call feedbacks. There are a lot of climatic feedbacks. I think one of the most famous and easy to understand is with the increase of temperatures due, say, for some processes through emission of fossil, of CO2, of CO, and it's converted then to CO2. You increase the temperature. But CO2 is not the only thing that increases. That increases the temperature. Okay, it's not the only greenhouse. But there's a very important greenhouse gas, which is methane. Okay, which is, and you have in Siberia, in the northern part of Siberia, there's a region called the permafrost. And what the name more or less says is what you expect, permanent frost. So it's a region that is permanently frozen. Okay, the soil is frozen. There's water and but it trapped a lot of methane. So if you increase the temperature and you have a smaller, and you begin to have less and less permafrost, you get more and more gases that will again get you on a higher temperature, which can enhance the production of CO2 by some processes here, and which will actually enhance would increase the loss of permafrost region, which increases again the temperature. So that's a loop. Okay, and you see that this drive you away from the present situation and take you to, in this case, to a warm Earth scenario. So this is exactly a feedback loop like the one that we have here. Okay, I mean it's buried in enormous models of climate change from climatic models, and you don't see a small this term and that term, but actually it is something of the kind that we have seen here. So. Yeah. Exactly. Yeah. Yes. Look, actually, last November and December or October, we were trying to find something realistic on this point. Not with this Klaus-Meyer model. Klaus-Meyer is for semi-arid. Amazon is not semi-arid. But I mean, you could, let's see. So I actually studied a lot about how you get this kind of situation of the Amazon. So what is, well, it's a pretty much complex thing. But the rain that rains in the Amazonian forest is, half of it is produced by the evapotranspiration of the forest. So it's local. And the other half comes from somewhere, okay? Which is the Atlantic Ocean. And this all gets more or less trapped because you have the Andes, which don't, and you have a desert on the other side because it gets trapped. So now, the evapotranspiration is probably somehow proportional to the number of trees you have. I don't know if this is a linear or non-linear relation. I have no idea. But then you get also something that gets out of this. And this is the flying river thing. That is the moisture that comes down to the southeast of Brazil, here, and mainly also the province of the state, Paraná and Mato Grosso, and it rains and so on. You have agriculture, and you're happy with that, and so on. You don't see it, but yeah, no. We have seen this last year, okay? We have seen the effect of this in São Paulo. We got a night, almost night situation at 3:00 p.m., and this was related to moisture circulation coming from the Amazonas and getting and getting in contact with the burning forests, and then it get mixed. And when it arrived here, well, it got trapped because there were a front. Okay, so well, more or less. So so there's water getting out of the Amazonas. So good. So it seems something something which is in equilibrium in principle. So, but there is a point, and if you go for the equations of hydrodynamics or atmospheric dynamics, if you have a kind of local convection, I mean, the water gets out of the region where the trees are, it goes up in the atmosphere, you have condensation and precipitation, and so you have convection, local convection. It's not the large-scale convection that cells that exist in the water you have heard about. It's a local convection. But local convection creates gradients of pressure at the middle atmosphere. And such a way that you have a smaller pressure in the region where the water is, in the region of the where this water gets circulating in the atmosphere, you have a lower pressure. What is lower pressure means that is a sink which attracts the currents from the Amazonas. So it's nice. So they will keep going. Now, you can have a feedback like if you cut down a part of the forest, okay, then you would say, will everything be just proportional? No, not exactly proportional. Why? Well, the flying rivers will be smaller. You would say maybe this is still some situation which is in equilibrium, but the fact that this gradient of pressure will be smaller and smaller, then you don't get any more a lot of water coming from the Atlantic. And then, due to this kind of nonlinear interaction between water and vegetation, cross a tipping point where you have enough water because the pressure, the difference between the Atlantic region and the Amazonian region is not enough to kind of suck all the water that you need, and then you end on a cycle that gives you no vegetation. So this is one of the things. It is interesting to look at that. And actually, I was trying to find for pedagogical, for didactic reasons, a very simple model with 2 or 3 equations, like this one. And we simplified everything, okay? But yeah, it would be nice to have something that could explain that where does the tipping point come from? Like, with some equations. It would be nice, for instance, I could substitute this lecture for a lecture about something more timely. So, but we couldn't. I mean, we didn't know very strong effort neither, but anyhow. But so where do people, I mean, if we couldn't, we obviously looked for the literature on that, and we found nothing about simple mathematical models. So where does the result come from? From global circulation models. So you have the whole hydrodynamics, the whole atmosphere dynamics, the whole budget of energy budget, the albedo and everything and so on. And so this is very complicated models running on supercomputers and so on. And so you can study scenarios. And people study scenarios of deforestation and see what happens, and you see the tipping point. So this is the work of people like Carlos Nobre and Thomas Lovejoy and so on, which are now very, very, I mean, famous persons here. Yeah, here this is just a rewording resilient situation in this setting is just a stable state. That this state is resilient and loses resilience, and here this state is resilient. So resilient is a small perturbation, and so on. Okay. It's not the only tipping point-like thing that you can have. You can have other transitions also, which are not due to this variation of a parameter, but due to stochasticity. You could think about a ball bouncing here, so it bounces here. So this point is stable. Yeah, nice. I mean, it's stable. Say it's marginally stable. So it goes here, but then you start to kick, tuck, 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 and then well, it's still what you will get. You will get a distribution of the positions of the ball. You take it at certain time steps, and you make a histogram. You will get something. If you tip with a Gaussian noise, you will get some Gaussian here distribution of the positions over time. Over certain, you make time windows, and you see where the ball is. Okay, this is easy to imagine. Okay, now if it's a Gaussian, maybe something at a certain point, if you wait long enough, there will be a strong enough bound on the perturbation on the ball that will take them here. Okay, so you have the loss of stability, the loss of not of stability, the loss of resilience of this point, where you could see this is a resilient thing, because I mean it is under perturbation, and it's all the time stable. All the time it's stable. But well, with a certain perturbation, it took you here, and then you stay here all the time. And so maybe at a certain point you get back, and so on. So you will have two processes. One process is described well by a distribution like that one, but there's a process on a different scale, which is rare events. So there are people that in statistics, there's the statistics of rare events, okay, which is very nice and very interesting actually subject, because you will have this kind of distribution, but sometimes you flip. Okay, so it's a way of losing resilience in systems, which is not here the same thing. I mean, you could imagine something like that, but here I had a parameter which is varying. Here I don't have any variable parameter. It's intrinsic to the system. It has two fixed points, but you could go from one fixed point to the other fixed point due to noise. Okay, so this is another kind of tipping point, which is also interested to study, and this is actually something, this kind of situation it poses real questions for people that manage systems, environmental systems, hydropower facilities, and this kind of thing, because when you build something and it is on a time scale which is short, say 50 years, okay? So maybe you have never transitioned here. So you think that the world is composed of only one well. That's what you would expect. Okay? I have not transitioned because, well, I have no way to know that there exists another world. Okay? And from the point of view of people that manage systems and so on, okay, this is a catastrophic situation, and this also shows you the model, the value of models, and the value of data. So incomplete data means, in this case, not having an infinite time series, could give you the impression that your system obeys a distribution here, which is a Gaussian. Okay? But if you have a good model, maybe you could suspect the existence of a second well. Okay? That would be an utility, actually, from using models. I mean, it's not easy to do this kind of thing, but anyhow. So that's also, okay, thank you for reminding me the word resilience, which is also pretty much used, okay? So, okay, so you see, with a simple illustration and with a simple example, we can actually understand a lot of things that you hear about when you look, I mean, you look, say, you open Nature on the part of comments and discussions or science and so on, you say, this and that and so on, and then you don't know what the meaning, what is a tipping point, what is tipping, what is not tipping. So everything is here in a very simplified way. You can have an idea of what people are talking about. So real world climate going back to climate research, the standard is using supercomputers with full models, okay? This kind of simplification that mathematicians and physicists like, it's seen a little bit like, okay, we can have a supercomputer. Why should we go for the simplification if you can take the whole system, okay? And actually this works. You have climate models that take into account every process on Earth, and you have a bunch of them. I mean, less than 10, but because these are big efforts, big teams, and so on. But while people do this and so on, but this is interesting because from the basic science point of view, you want to understand things actually. Okay? From an applied point of view, you want the results in order to have, be able to influence policies. Okay? So from a basic point of view, all these super big computer models, they have their value, but you would like to understand better this sometimes with smaller models, which just as we have done here somehow, okay? And we have smaller models, but we get the essence of the effects in these models, okay? So this it allows you to understand the things, where the things come from, and so on. So here we could understand very easily what's a feedback loop with just one term and equations. So, but obviously this is good for basic science, a basic understanding of science, which, I mean, this could obviously illuminate also the applied side. But if you really are like in the situation we are today, we don't want just the basic science. We just want people that actually are able to tell a lawmaker what the situation is. And this can be done only by convincing people that you have good models and so on. So climate deniers, like our Minister of Foreign Relations, they say that the models are wrong. And this is egregious. I mean, this is very, if you look what IPCC, the Intergovernmental Panel of Climate Change, has done as works, it is fantastic, scientifically. It is really, really amazing. And when you read the whole report, the whole sections, these people have been through every hypothesis possible and trying. And you know the hell of parameters, they have a hell, but they manage the hell, and they get limits for things. It's very serious models, and there's not only one model, there are several models which have a little bit different hypotheses, okay? So, but there's no such thing as a 100% precise scientific result, okay? In general, everything has some error, and climate deniers use the same tactics as people, as the industry of tobacco used. It's saying that we don't want results that have no precision. We will act only when we have precision. Therefore, we cannot take these results as reliable. So if the world had done this in the past, we ought be in the ages of, I don't know, and we not have been out of the Middle Ages, or even not out of caverns. So using results that are imperfect is normal. Okay? If you want to build a building, it has also some uncertainties. You can manage uncertainty, which is a part of applied math and statistics, is management of uncertainties. So you build up a building is built with the possibility that it's just breaking down. It's 1 in 1 million of years. Okay, so you manage the uncertainty such that, well, you expect it not to break down. So So again, you can estimate uncertainties and so on, but people from IPCC also do. So saying that the models are not precise, it's the same. Actually, there's a very interesting story about that the people involved in the beginning of climate change denial were actually people that were connected to same that have been involved with the tobacco industry, which said, okay, we don't know if smoking gives you cancer because there's always a possibility. And then what you get is there's always some guy, which maybe the guy is just an idiot, or maybe the guy is just making money from the industries, to say that there's an alternative version. Okay? And this happens with tobacco industry. There were results which then, years later, turned out that the people have been paid by the industry and these results were published and said that, well, there's not such a problem and so on and so on. Everything in a more or less scientific thing, but it's actually garbage. And that's more or less the same. There's a guy in the United States that denies that the models are okay. Well, all of this goes into some very good scientific things because the guy used to be a good scientist, and he just sold his soul to the devil, and so he was respected, and so he can say that there's no anthropic origin of climate change of heating of Earth, and so this creates a lot of confusion, which and then you say, oh, we have to hear both sides. In this case, you don't have to hear both sides because there are 100 sides, but 99 agree and 1 does not. So, but you see, this story about models is interesting. So we, as sometimes looking for the pleasure of understanding things, we would prefer some simplifications. And this is good, and it's advanced science also, but then you also need, on the other hand, when you go to not only applicable science, but actually applications of science, and in this case, actual application means these big models. This is also important and can be made in a sound way. The effort in the case of climate change for IPCC is really scientifically very, very good. Yeah. So, okay, lots of talk. I don't have anything else. I just have here some bibliography. In this case, it's very different bibliography. If you are interested, there's nice things. So there's Schaeffer and Carpenter, Catastrophic Regime Shifts in Ecosystem, Link Intuitive Observation. So this is in general. It's not for desertification. Then you have the paper of Klausmeier from '99. Ritkert, this is also a paper on vegetation dynamics. And then there's this also, Sherrod. And okay, this is a book by Schaeffer, which is without equations. It's just talking things, okay? So just, okay, let me mention something. You would like to have elements to predict that you are close to a tipping point. Isn't that nice, okay? Are we close or not to a tipping point, okay? So say, God back, I'm living here. I know nothing about this, okay? Are there measurements? Are there anything I can do such that I know that I'm close to that, okay? In the case of desertification, it's very difficult to really revert the situation. But in other cases, and a place where you have this kind of situation is lake eutrophication, and then you could take action, okay? And oh, this is called almost a whole area, or it's a subject of research mainly by people like Schaeffer and others, which is called the early warning signals of catastrophic transitions, okay? It's phrased with a little bit colorful words, but early warning. So early warning would be super good. So there has been a development of that by a group of SAIFR and other people about early warning signals. So they use the fact that you are all the time under perturbations, okay? And one thing you can show is that the time it takes from perturbation to go back to the stable state increases when you are near this pink, okay? And also the autocorrelation functions of step 1 has a peak at the transition. You could use this to look for early warning signals of critical transitions in all kinds of systems. This can be done. And actually, this proposal turned out not to work the way that people wanted. It is true, mathematically, in the models, and so on, and the signals are there, but usually what you see is not early. It is when you have the transition. You have signals that characterize the transition. You would say, I would like to know this before, so I can take action to avoid a transition that I don't want, but yeah, the proposed early warning signals by SAIFR and company, they are actually, they are together with the transition. So they haven't, I mean, all of this is still good science in the sense that they may characterize the transition as happening. That's nice. But they are not predictors. For the particular case of vegetation dynamics, not now, I'm not talking about general systems which have tipping points, there is the spatial aspect of vegetation that has not been taken into account here. But people have shown that when you are with plenty of rain, you have a fully covered region. But if you start to decrease, then you get like stripes of vegetation. When you are here, you just get some points of vegetation. So this could be used as early warning in this particular case because there is a spatial dimension. Okay? So you make aerial photographs, and you look for the vegetation pattern. So this is another very interesting topic. It's how are the patterns of vegetation formed. So therefore, this would be spatial vegetation dynamics, which Ricardo here Martinez is a specialist and so on. This is also a very nice thing. So you could think at this kind of a situation where you have this, you are close to transition, okay? This is one possibility. But in many systems, in many cases, people are looking for this kind of thing. Can I have, from a practical point of view, I want to have an early enough signal that tells me that I'm in trouble. Okay? So thank you for staying until this last class. We will now have your pretty good afternoon where you will finish your work, and tomorrow at 10. But please be on time, because we have a schedule, yeah? So actually, it's a tough schedule. I mean, we start at 10 and we go up to 5:30, with 1 hour and 30 minutes for lunch only. So I don't want to start 10:20, okay? There's no space for things. I mean, if we start late, we have no time for lunch, okay? Which is very bad. And so today is your day of preparing presentation, or finishing the work and preparing the presentation. So good luck. And so we meet here tomorrow at 10. Thank you.